Ever wondered what stops a massive chemical plant from turning into a disaster zone? Well, it's not just the people sitting in the control room. There's this hidden safety net, an automated guardian angel, and it's all governed by some surprisingly elegant math. Today, we're going to pull back the curtain on functional safety. We're talking about the engineering and the actual equations designed to prevent the unthinkable. So here's our game plan for today. We're going to start with the really high stakes, why these systems absolutely cannot fail. Then we'll get into the automatic safety net that engineers have built. After that, we'll look at some seriously clever design strategies before we dive into the heart of it all, the math of failure. That's where we'll see how numbers can actually prove a system is safe. And finally, we'll see how it all comes together in the real world. All right, first things first, let's set the scene. You have to understand that these big industrial plants are places of just immense power, and because of that, potential danger. A place where human oversight on its own just isn't going to cut it. I mean, just think about the forces at play here. Engineers are constantly wrestling with enormous pressures, incredibly high temperatures, invisible but deadly toxic gases, and yeah, the constant threat of explosions. In an environment like this, a catastrophic failure isn't some rare possibility. It's a constant variable that has to be managed literally every single second. And when things go wrong, they go really wrong. Horrific disasters like the Bhopal gas tragedy or the Deepwater Horizon oil spill are just these grim, painful reminders of what happens when these protections either fail or, even worse, aren't there in the first place. This is exactly why having robust, automatic safety systems isn't just a nice to have. It's an absolute non-negotiable necessity. So how do you do it? How do you create a safety net that's faster, more reliable, and just more vigilant than any human operator could ever hope to be? Well, the answer is you take the human out of the immediate loop. You create an automated system that's designed to act decisively at that single most critical moment. And that brings us to this core philosophy, functional safety. A great way to think about it is like the airbags in your car. You don't get to decide when they go off. The car detects a dangerous condition, a crash, and the system acts automatically, instantly, to protect you. The goal here is exactly the same. Get the plant to a safe state without waiting for a person to notice and flip a switch. And the actual tool that puts this whole philosophy into practice is called the Safety Instrumented System, or SIS for short. Think of it as the plant's own guardian angel, a totally separate, dedicated system whose one and only job is to watch for danger and jump in when it's needed. Now, any SIS, no matter how complex, has three basic parts that work together in a chain. First, you have a sensor. Its job is to detect the hazard. Second, you've got a logic solver. Think of it like a specialized, super reliable computer that processes the info and decides what to do. And finally, the final element is what actually carries out the action, like an emergency valve slamming shut. Sensor, brain, muscle. Okay, so a big plant won't just have one giant safety system. The main safety instrumented system, the SIS, is kind of like the whole nervous system. It's made up of lots of individual reflex arcs, and each one is called a safety instrumented function, or SIF. So you might have one SIF dedicated to watching for high pressure. Another one is totally focused on detecting a gas leak. Each one has a single vital mission to accomplish. Now, here's where it gets really, really interesting. It's not just about having the parts, it's about how you arrange them. The actual design of these functions is what truly determines how reliable they are. This is where strategy becomes everything. So, on one side, you've got the simplest approach. 1 out of 1. One sensor, one decision. It's simple, sure, but it's brittle. If that one component fails, your whole safety net is just gone. But then on the right, this is where things get really clever. 2 out of 3 voting. Here, you use 3 sensors, but you only need 2 of them to agree that there's danger. This introduces redundancy, and believe me, it is a complete game changer for reliability. So how does this voting actually work? Well, imagine 3 sensors are all watching a reactor's temperature. Let's say one of them glitches and sends a bad reading. It doesn't matter. The other 2 sensors still see the real danger. They outvote the faulty one, and boom, the system triggers the safety action correctly. It has a built-in tolerance for failure. And now we get to the real heart of it all. How do engineers prove that one design is actually safer than another? Well, they don't guess. They use math. They use it to calculate the precise probability of failure. The magic number that everyone in this field is chasing is called PFD average. It stands for average probability of failure on demand. Now, forget the jargon for a second. All it does is answer one simple, incredibly crucial question. If a crisis happens right this second, what are the odds that this safety system won't work? And the goal, obviously, is to make that number as close to zero as humanly possible. So let's start with our simple 1 out of 1 system. The formula to figure out its probability of failure looks like this. Now, it might look simple, but every single part of this equation tells a critical story. It tells us that the PFD is basically a function of two things: how often a device is expected to fail, that's called lambda d, and how often we check on it, which is TI. Let's break those down. So, lambda d, that's the dangerous failure rate. It's the rate at which a device is expected to fail in a bad way, and it's measured in failures per year. And TI is the proof test interval, basically how often you test the system to make sure it's still good to go, measured in years. You put those two together and you can calculate the PFD. Okay, let's make this real. Let's say we have a valve with a known failure rate, our lambda d of 0.1 per year. That means, on average, we expect it to fail dangerously about once every decade. And let's say our policy is to test it every 6 months, so our TI is 0.5 years. We plug those numbers into our simple formula, do the quick math, and we get a PFD of 0.025. So what does 0.025 actually mean? It means that every single time a crisis demands that valve to shut, there is a 2.5% chance it will fail. That's a 1 in 40 chance of disaster. Now, those might be pretty good odds for a lottery ticket, but when you're dealing with a chemical plant, is 1 in 40 really good enough? I think we all know the answer is no. Okay, now watch this. Let's see what happens when we use our 2 out of 3 voting design. The formula gets a bit more complicated, but a simplified version shows the most important change. Look at that. We're now squaring that core term of failure rate times the test interval. And if you remember from school, squaring a small decimal makes it dramatically smaller. This right here is the mathematical key to a massive leap in safety. And here is the payoff. Just look at this comparison. With the exact same valve that has the exact same individual chance of failure, simply by arranging them in a smarter, redundant architecture, our probability of failure just plummets. It drops all the way down to 0.0025. That's a 0.25% chance of failure. We have made the system 10 times safer, not by building a better valve, but just by using math and a clever design. It's not a guess, it is a mathematical guarantee. So the whole point, the crucial step, is connecting this math back to the physical world. Let's trace one complete safety function from start to finish to see how all these pieces come together to prevent a real disaster. So imagine, a reactor is overheating. The temperature starts to climb dangerously. 2 of the 3 sensors pick it up and they vote to trip the system. The logic solver confirms their signal and immediately commands the final element, an emergency valve, to open up. Cooling water floods the reactor, the temperature drops like a stone, and the plant is returned to a safe state. Disaster averted. All thanks to engineering and math working in perfect harmony. So, the next time you see one of those massive industrial plants, don't just see the pipes and the steam. See the invisible layers of protection, the redundant systems, and the elegant math that's working silently in the background, keeping everything in check. It kind of makes you wonder, doesn't it? What other parts of our world, from the autopilot on a plane to the power grid in your city, are being kept safe by nothing more than a clever equation?